Welcome to the panel on systems engineering, the solution for the limits of Dennard scaling and Moore's law. I'm just going to give a little bit of the description of the event. With the increasing semiconductor content in multi-domain systems, the overall system characteristics are largely determined by the overlap of SoC and physical systems. In a software-defined world, the systems themselves become a constant trade-off between the physical, semiconductor, and software worlds, whether we're talking about an SoC, an autonomous vehicle, or an automated factory. So in our case, we're going to be exploring some of the ways that we can either address, circumvent, or work with Moore's law and Dennard scaling, because we will continue to move forward as far and as fast as we can, and because of the nature of our industry, any opportunities that we can discover to address these issues, we're going to implement. We're going to talk about some of them here, and open to questions from the audience as well, because it is an issue that impacts us all at every level. So before I go on, I'm going to let each of our panelists introduce themselves, say your name and a little bit about yourself for the audience.
Sure. I'm Puya Yagini. I'm working at SpaceX Starlink. I'm managing the pure silicon verification, emulation, validation, and my background is in computer architecture.
Mark Malinowski. I'm with Siemens EDA. For the last 3.5 years, I've been leading the systems engineering initiative within the electronics design automation segment. My background is a number of different roles and responsibilities in companies producing complex systems, primarily for diagnosis and manufacturing testing of semiconductors. In the last 6+ years, I've focused on this area of the needs of systems engineering and electronics.
I'm Larry Williams. I'm a distinguished engineer at ANSYS. I've been with the company for a long time. My background is electromagnetics, so I came up driving HFSS was my core of my career. But then into product management. These days, I look across physics and delve into systems, working with our top customers, building strategies on how they may implement advanced engineering simulation in their processes.
And Brett Hillhouse with IBM. I'm in our IBM's sustainability software organization. I'm responsible for industry strategy. Background is more in the aerospace engineering side of things, but I've been involved in systems engineering and engineering process for 25 years plus. With a background coming out of some of the other engineering companies that are represented here today.
And I'm your moderator, Alex Pault. I'm with electronic design and microwaves and RF. So let's start this by recognizing that we're not necessarily going to get to 0.5 nanometer scale architecture, right? Recognizing that we may not be able to brute force our way through this. Let's start with our first question, one of our first seed questions. Of course, as I said, if anyone has a question, raise your hand. We'll have you come up to the microphone and ask. But let's start it by just saying, what are your thoughts? And why don't we have one of our system guys jump in first? You can jump in first. But can we engineer the chips to address this issue? I mean, we talk about 3-dimensional scale, chips and chiplets and things of that nature. What are your thoughts on how we can best address these needs just by making better chip architectures?
So I'll do one. So at IBM, we are doing some interesting architectures from a chip design perspective. So one of the thoughts here is, when I'm doing AI algorithms, I'm looking for a level of confidence that my decision is right. I don't need a great deal of precision in my computing. So there are ways of actually, making it a less accurate computer, but still get a ton of more throughput through it. So the idea of looking at the type of algorithms, the type of software you want to run, and are there more interesting architectures that possibly could be used for that?
Mm-hmm. Oh, that's a good observation, Brett. How about you, Larry?
So, adding on to what Brett said, I found it quite interesting. Maybe some of you folks watch the Veritasium YouTube channel, where he goes out and finds various physics problems to solve. And on that, one of his videos, he mentioned what you were just mentioning, Brett, about using different architectures for AI. And in particular, I thought it interesting, a startup company called Mystic AI that's doing analog computing. So using an analog computer because it may not need that precision, as you mentioned. Maybe that's an interesting way to go. Of course, what we look at is some other things, a trend that we've recognized is something we call bespoke silicon. So silicon that's being designed specifically by a company they want to build something that gives them a technological or competitive advantage because it's truly custom for their system design. And we see, whereas it used to be, we'd have only semiconductor companies producing universal chips. Now we see companies like Facebook or Amazon who are systems experts designing a chip to work in their system. So I think we're already down this road that you mentioned, Alex.
Yeah, we definitely have started going down this road. And it's an interesting point you bring up, Larry, about analog. Because one of the interesting aspects of an analog circuit is you can improve the circuit, simplify the circuit, and shrink its size, right? So circuit optimization is also an aspect of it. What are your thoughts, Mark?
When we started our initiative, it was responding to customers who asked for our plan for MBSE. And what we found was that there's two completely different conversations going on, whether you're inside the EDA space, speaking outward, or outside of the EDA space, trying to get those stubborn electronics guys to just play ball with us, right? And what we realized was there wasn't much systems engineering in electronics because it wasn't good enough for electronics. The systems engineering practices weren't model-based enough. And so we went about trying to understand what would close that gap, and we hit on this problem, is that slowing of scaling is at least contributing to more customization. And when you express system of interest functionality in custom electronics, you have to know what that electronic system is going to do in that system. Now, if you look at our systems, you have platform levels, you have compute box levels, and you've got silicon levels. Well, everybody that's working at those levels of constituent subsystems it's their system. But we've got to get verification of the system behavior out of the design and verification of each of those flows now that we're tying the requirements together. And that's what we see as the daunting challenge right now. How do we get system functional verification out of the silicon design and verification flow?
Excellent. That's an excellent point. Now, Horia, SpaceX is known for being cutting edge and doing some very interesting things. Are you all looking at it at all from your point of view?
Yeah. So for our application, not the rocket side SpaceX, just Starlink side, that's a challenge as well. Scaling, just putting server class type of computing into space. That's a challenge. Some people mentioned here relaxing the requirements, and then you mentioned 3D chiplets. You see all around the conference, everyone is talking about chiplets as well. One thing that no one is talking about is training the software engineers. You may go and then build the most powerful machine, give an exascale machine to a software engineer, but when he is not writing a code which can leverage, or he's not optimizing the code to the factor that it should, it's like waste of resources, right? We try to, what we do is we collaborate with the software team at all levels to make sure that when we architecture the chip, we will add more computation, but maybe we can take other approaches, like finding out how the application is, how the software engine is going to leverage. And also maybe we can give them some better interfaces to optimize their software. But all these needs to happen together. So relaxing the requirement, there might be some dumb requirements always coming from different people. You need to push them back. Increasing the real estate on the silicon, no one can avoid it. So either through chiplet, 2.5D, MCM, you have to go with that. Also, taking it one more level on the board, also that's another thing that we have taken. On the analog one, it's a bit challenging if you don't go 3D. If you go 3D, it may work, though the yield might be down. I'm not an expert, but what we've seen going down the process towards 4.3, analog doesn't scale as much. The libraries are not characterized for. So that's another challenge. But these are good ideas.
Well, and that you're right. So, so that ties into something we were going to, some other questions, but let's go ahead and, since we're in this path, let's roll with it. When you think about the whole aspect of the issue of hardware, the issue of software, and we'll tie it into the second question, which I was going to ask about circuit design. Let's step away from the chip and think, well, okay, if we can't do anything on chip, what can we do on the board? So I would say, Brett, what are your thoughts on that? IBM, big powerhouse computing company. What are you doing at the board level to address these issues?
Well, I want to hit on something you mentioned on the software side of that equation, because I still think that's really important. The vast majority of from what I see, and I won't speak for your company, but from the vast majority of what I see in the type of code that aerospace and automotive companies create, it is hand code, all right? It's not very well written. It's crazy the way they're doing it. They're not doing a model driven. They're not doing it with auto code generation. There's a huge amount of opportunity there in just modernizing the process and doing a hell of a lot better job of creating modern code. And I think that's something that we haven't looked at in the industry very strongly yet.
Well, Larry, what are your thoughts on that?
Well, I'd add on to that is that code, especially for aerospace applications, has to meet numerous requirements for safety, and that code has to be generated. And one way to do that is to have an automatic code generator that already meets those safety requirements, the ISO, for example, or say in aerospace. There's automotive AUTOSAR standards also, and so I agree with you, Brett. That makes sense to be able to drive that. But to answer your question about printed circuits, one of the things I've seen in our customer base is a greater push towards automation of verifying circuit board behavior. So you have thermal requirements, you have, of course, signal integrity, power integrity requirements, and the ever-daunting EMI, right? You find out at the end of your development program that you won't meet EMI. That's the wrong time to find out about it. So we've seen a lot of our major customers will build automated workflows that automatically, read in the database from your EDA layout, cascade together, drivers, receivers, look at that high-speed electronics, try to understand whether or not you have pass or fail, and even produce an automated report. And we've a lot of companies adopting a Python-based programming approach for printed circuit boards in particular. Make sure they meet requirements.
Well, Mark, you're also a systems level guy, right? What are your thoughts on that whole aspect of the board, making the board address the issues?
Yeah. Understanding the functionality that's the goal of the system of interest eventually translates into some kind of allocation, right? So you're going to allocate functionality to some system elements. This issue of having the right expertise of writing software in the context of can that hardware execute it fast enough under all conditions that system's going to find itself in is a very difficult type of engineering. So we've been trying to target this area by labeling it as a new type of problem. We call it cybertronics design automation, because you have to have this architectural understanding of the functionality, how it's allocated before you even know if it's hardware or software yet. So building a logical architecture, doing some real analytics against it so you can get KPIs out that drives your decisions of, is it monolithic silicon? Is it a chiplet-based system and package? Is it a bunch of chips on a printed circuit board? You can make intelligent trade-offs with some analysis behind it.
Excellent point, excellent point. Well, Puriya, when you mentioned about the satellites, space, size, weight, and power, right? Swap. It's all there anyway, so you've got to address that no matter what the goal is, whether you're trying to beat Moore's Law or just make that satellite smaller.
So satellites can be smaller because we need more power. If you need more computation and power, you need more power in terms of solar panels, right? The satellites grow. So that's something that we have to deal with. One other challenge that no one has mentioned here yet is the thermal dissipation for us. The more computation you're bringing into the chip, the lower process that you go, everyone knows power consumption goes higher and hence the thermal. While you're in the ground, who cares? Put a cooler, put a fan on, huge fans. But when you're in space, there's no fan. What would you want to do with that thermal density? And that's another challenge which we are dealing with.
How are you dealing with it at the present time?
Again, I'm not that expert on that, but the only way to dissipate the temperature thermal is the radiation. You need to radiate it out somehow with the materials that you're using. But let's say you have a really tiny chip, not one actually, but lots of those, maybe hundreds of those on multiple boards, and then now you want to dissipate all those temperatures out. That's a challenge we're dealing with. Some of them that are in the space, they work fine. We have tackled. We're working on new generation of the chip, which we are analyzing. So it's not up yet. I can't tell you if our ideas are going to work on or not, but I'll let you know in 2 years.
Oh, I'll wait. I'll be there.
Okay.
Now,
Alex, I want to.
Yeah, go ahead.
I'd like to add to what Puri was just saying, and that
Please.
is, if you have a spacecraft in space, it also matters the mission itself. That is to say, the trajectory this craft is following, and do you roll the craft to? Maybe you can reposition the solar panels, but maybe you roll the craft so you can get more of this radiation away from it, depending upon how you choose. That's certainly a system level issue that could affect the thermal, right?
Or you can throttle, right? You can throttle back.
Throttle back
yeah.
the computations.
Yeah.
well, and those are both great points. But then, in fact, one of the aspects about thermal, and I'm very fond of saying it, anybody who knows me talk about power, is power management, thermal management are almost the same thing anyway. And one of the most easy ways, in my opinion, to address thermal is run more efficiently. The less waste heat, the more efficient you run, the waste heat is less, so there's less issue of dealing with waste heat, which kind of ties back into addressing with chip architectures and system architectures. If I can make a more efficient circuit, I don't need as much thermal management, right?
Yeah, that's true. But when you go at board level, you mentioned board level, you asked, you're distributing the computation. Now, if you want a software which is control of the entire computation, or you want to have having standalone software running just without talking with each other. If it's just the monolithic software running on multiple chips, then you're increasing the communication between these chips. Going off chip burns more power, right? And then hence there's another consideration you need to make on where is the balance in terms of scaling out on the board versus bringing in the computation within the chip.
Well, Brett, again, back to, since we're talking, into that whole aspect of computing, and what do you see as the big chase in the balance between efficiency, thermal management, power management, space, weight, size?
Well, I mean, that is what systems modeling came out of, right? It was for doing trade studies. I mean, that's really what we're looking at. What are the types of architectures? What are the type of trades that I might make in power consumption versus, accuracy of the computational elements? It's not as straightforward as just allocation and you know where it is. It's an iterative process. You're going to go through and you're going to try some of these things. I think what this does is it starts to suggest that our waterfall approach for doing ICs is not necessarily met well with this type of an approach. And I think we have to start looking at, how do I do a more agile approach, or one that's at least an iterative process in order to be able to do those trades over time. And then as I get more fidelity in my system model, and I understand what my accuracy is, I might have to make some trades. But that means I got to have traceability. I have to understand my requirements that those elements are meeting. and I have to be able to make sure I'm tying that into your test cases. It's understanding all your engineering artifacts associated with it and keeping those under some sort of configuration control. And that's something we've been working with Mark and his team on, understanding how do we work some of these system level disciplines into a domain specific area. We've done that in software, we've done that to an extent in electrical, but not really into the electronic side of things.
Excellent observation. Now, before we go on, are there any questions from the audience before I go to another one of my questions? Well then, let us continue. Now, Mark, we've been bouncing around the question, but let's bring it up graphically. It's one of the panel questions. How does the resource situation change the way we optimize systems between a hardware engineer and a software engineer aspect, right? You're almost pitting the two against each other, even though they're supposed to also be collaborating and refining each other's processes.
Yeah, what we've been dealing with is we've opened up more dependency on bespoke microelectronics to the system behavior. We're causing the trade space to just explode unmanageably. And so what everybody seems to be doing is you make some educated guesses and you go. And there's not real good methods and tools for continuously checking that, as Brett was describing. And there's been some fairly significant, spectacular failures that have come out of some projects as a result of that problem. So the way we're attacking it, it's not a perfect solution, but if we can carve that trade space back down to something we're used to dealing with, then we have a chance of having architectures that'll hold up and perform as we're expecting. So we're going after the digital computing aspects and making sure we've got the margin that if we can't get that to run on core X, Y, or Z, then get it into custom electronics. Power goes down, space goes down. Yeah, you got the cost and the additional challenge of design engineers available to do it, but you have a better chance of keeping your program under control.
Also good points. Now, Larry, do we throw the hardware and software engineers into an arena and have them just duke it out and then
cage fight?
Yeah, cage fight. Because both sides have legitimate arguments. The software people are saying that they can solve the problem. The hardware people are saying they can address the problem. Where do you draw the line between, okay, we want to beat Moore's law. We're not just trying to create we want to make a better product at the end of the day. We're not just trying to have an engineer contest, as it were.
I mean, it does boil down to an engineering trade, right? So if you have, like in the case of, let's say, an RF communication system, right? There's a big trade-off among how much prime power can you run on the transmitter, what kind of process do you need on the receiver low noise amplifier, how do you choose, can we maybe use a more simple semiconductor approach, but add more digital signal processing to recapture that channel gain that you need to do it. So it all is a balance between how you architect the system and how do you get there from here. Well, you get there from here by having a model-based approach to the whole system and have it possible for you to perform that design trade to say, all right, let's use a simpler semiconductor approach, lower RF power, but more signal processing on the receiver, let's say, for maybe some different signaling protocol, maybe some spread spectrum approach instead of a single clam type channel, depending on what you do, right? You have to make those trades. And the only way to do that is have a full sort of system architecture model that allows you to trade those off. Otherwise, I mean, in the old days, right? The old days, it was all written on paper specifications, and if you wanted to make that design trade, you had to use up some shoe leather to walk over to see the transmitter designer and I'd talk to him about it. Hey, can I get a couple of dBs here? No, I can't give you anymore. You have to go now. You got to go talk to the receiver guys and say, how about a little more noise figure so I can get my sensitivity back, right? So I think that the model-based approach, digitizing the approach, building all of those, the specifications are built into each subsystem that are going into that model.
Well, one of my jokes, I'll get right to you, Brett. I just want to make my witty comment and then I'll... No, actually, one of my jokes is half of what I know I learned in high-end audio. And if you want the speaker to sound well, you can either boost the power for the 3D or you can drop your noise floor by the 3dB and you're getting twice the power output just in that. So it ties directly into what you were saying. So Brett, what's your add-on on this?
So we've been doing a lot of this type of work, especially in automotive. There's a lot of change going on in the automotive world, as you all know, as consumers even. But what has been interesting is we needed something to bridge between the systems, the software, and the electrical teams. And we needed an ontology that allowed them to actually understand what each other is trying to accomplish. And AUTOSAR is one that has been leveraged pretty well in that industry. It helps me understand it down to the chip level as well as up through the OS and up to the application levels. So it gives me a level of description that I can use to transfer data between domains and so that I can actually talk. There's similar ones out there like AADL and FACE in the aerospace and defense industries. I think some level of looking at that type of a standard ontology and how you're going to bridge between the software teams and the chip teams and what they need to do, I think that's going to be necessary to get adoption. It's just too hard without that. And so I think ADL, Mark and I have talked about it a little bit. That's a possibility in this area.
We're gonna have to keep pushing, aren't we?
Yeah.
Now, Puri, what are your thoughts on this?
I'm going to change the subject a little bit. So going back to your previous question when you asked about the resources, or maybe this question just...
Well, they're related.
Yeah, hardware, software, resources. Software and hardware, based on what I see, they fight always with each other. You need someone to talk with their own language. Just be a mediator. And these are not the only two should be in the room. So architect and software, you need the verification team. And you need to have the program manager because they're the one who set the timeline and time to market. Time to market is not something like you're gonna sacrifice for getting a better chip, let's say in 5 years. No one is gonna accept it, right? So everything together, you need to put them in one room, let them fight, and then whoever comes out alive, that's the winner. On the software side, what I've seen is they'll make their points, but they go away. And then they're the architects who are gonna, at the end, build their product. And then software team, at least what I've seen is they will always nag, but they'll comply at the end.
Well, at the end of the day, you have to comply. We're all on the same team, right?
Exactly. Otherwise, the product won't be out within the time that you want.
Now, let's go ahead and follow on right there because you were talking about verification. As we move towards system-level optimization to address Moore's Law, to address size, to address power, to address all of these things, it does impact verification.
Completely.
So how do you see it changing the environment, the ecosystem for verification? Because now it's got to serve multiple masters.
It does. So in past, I've seen architects just being focused on power, area, and efficiency. Now these days, I've seen architects are saying, oh, we can use this because I know the VIP exists and the verification team will be happy. And then because they have seen lots of pushback in past, now they've learned their way. So verification is playing a key role in, at least in our architectures these days. We need to make sure like when we architect a chip, it complies with what verification team wants, and then the resources they have within a timeline that we have also. So verification for sure plays a major factor. Sometimes, or maybe I've seen, I've convinced architect to change the architecture because of the verification. So.
Well, it's a complicated situation. You're juggling a lot of different factors to get an optimal result. Right, Mark?
If you go back to the roots of systems engineering as a discipline, validate you're building the right system, verify that you're building it right. I mean, that's what the V diagram was trying to give us over the years. Now, if you look at what happens today, you have some generally closer alignment between those that call themselves systems people and those that call themselves software people, and nobody wants to talk to the electronics people. So how do you, what do you go after? You have to bring a methodology that can bridge that, whether it be leveraging things that have already worked like AutoSAR or AADL. We've gone, my group's gone all in on Arcadia because it gave us a really explicit way to break down functionality and then grouping that into a logical architecture and then doing your analysis to figure out what are the physical elements you're going to build and have all that hang together so that people can read that information and actually understand it. And that's been a big problem in the systems modeling that we've been working with today because it tended to be, at least for part of the reason, very software-centric. So we think we're attacking some of that now. We're seeing progress and improvements, and we can start making really good architectural decisions with a lot of information behind it as to why we did it so we don't relitigate it later and have yet another cage fight.
Makes all the sense in the world. Now, we have a question here, but I just want to ask really quickly, Larry or Brett, did you have anything you wanted to add to this point, or can we just move on?
Just one quick
Go right
thing.
ahead, Brett.
One thing that we have coming out is SysML v2, all right? It is much more amenable to dealing with physics versus dealing with software, okay? And so being able to deal with some of the types of trade studies that we're talking about and dealing with some of the specific trades that you're gonna have with regards to performance and EMI and everything else that you have in chip design, this is much better related to that and should be able to give us a big boost. And I know we're all in on that, on going out there and helping create that. But again, I think it's gonna need that ontology for each discipline to really be able to take it on.
And it's a crazy balancing act.
Yep.
Now, we have a question here. Please, give us your question, sir.
Yeah, I was wondering, are we going to be moving in EDA to software-defined systems? And I've been working a bit with the Open Compute project guys, and we're looking at how we design chiplet systems. And I'm kind of seeing the overlap between the board level and the chip guys, and I'm thinking, is that going to drive some consolidation in this industry?
Who would like to jump in first? Larry.
I was going to
Mark.
say,
I'll just add to the question, it's like, why are we building the chiplet-based system, right? And when I've gone into these conversations, people sometimes just look at each other. And right now there's two big camps. One is the people that are using chiplet-based designs to build product types that we already have, like better processors, right? Better processing components. And then there's the more visionary view of we've got this chiplet-based economy and we're just picking them up and plugging them together like Legos, and you pick a substrate that can handle it all and it just works, right? That looks like a ways off. So what are we doing in the meantime? We're trying to figure out what that mix is of how we can stretch non-monolithic IC designs a bit further in a reliable way that doesn't overly risk the project. It's still taking a lot of work and a lot of know-how that's not terribly common in the industry yet.
Larry, Brett?
what was the question on software designing the
Well, it's
systems
companies
and
like Meta, like to do stuff from a software level and automate down from there. And they're also involved in Open Compute, where we're looking at building HPC systems and things. And there's a lot of performance in packing things in smaller spaces, which is where the chiplet stuff comes in. So is that going to drive a consolidation in the industry between people that have been doing boards and people doing chips now that they're together on chiplet systems?
Well, certainly we know that bringing together those systems has its own set of challenges, even beyond the integration challenges for electrothermal, parasitics, extracting the heat, even mechanical reliability of a 3D IC, for example, has its own set of challenges, even beyond the software. But you weren't asking about software design, like an AI-based design of digital circuits, is that?
We're looking at that as well in the Open Compute project, but I wouldn't say it's gone anywhere yet.
I think the only thing,
Go ahead, Brett.
thing I would add is just we have to think about what some of these industries are trying to do right now. And even in aerospace, I see a lot more about software-defined vehicles. No, not just the auto industry. And I think we have to look at what does that mean, because it means I need more portable software. I need to be able to update things over time. It's a different kind of software model and flexibility that you need to build into your system. So if we're going down chiplet path or anything else, how do I make sure that this is going to be a system that is going to be very easy to be used in that kind of an environment? Is it really supporting that type of a vehicle program where I want to move software perhaps from one part of the computing area to another based upon performance characteristics? It adds just another level of complexity.
So Puriya, let you have last licks on this question.
I didn't get quite the breadth of the question, but what I understood, you're asking coming from software down to the chip, how does it work, or how to find out if we need a chiplet or not?
My personal opinion is the future is software-defined hardware rather than RTL out, which we seem to have at the moment.
Software, okay.
And then there's
That's an ambitious type of goal. I've seen it like HLS, or it's been around for a really long time.
I think AI may help us do it. So we might
Let me ask you this. Do you put your faith into AI to build a, let's say, tens of $million chip today?
I do
Future
verification.
maybe.
So my focus is verifying whatever the AI creates actually does what it's supposed to.
Well,
Okay.
I would say that it was a good question to bring up. Unfortunately, it's such a deep question, we could almost make the rest of the afternoon on it, but there are a couple of people with some more questions, so let's go ahead and hear a couple of them because we've only got about 10 minutes left in the session. How about you, sir?
Yeah, I'm Srikanth, founder of a company called Savia, just relocated to Bay Area to start an operation here. The question is to Puriya. I see that you're managing to get enough time to teach at UCI some subjects. Nice to know. That's good inspiration. My question is the way we handle the education of system design, electronics design in the college, in the university system. There are so many silos, right? People do hardware. Within that, there's physical design, there's digital design, front end, back end, and then there is system guys. System guys are so-called, kind of gods, demigods. We have to come out of this, I feel, just like the software guys are getting rid of, database guys, back end guys, full stack, they're going, right, all the way. Yeah. What do you see there, the evolution, the trends, and make it easy to design stuff?
That's a great question. Yeah. Because based on what I see is the education in terms of coming from systems to chip design is completely broken. Yeah. Everyone does. So if we want to fix it, first we need to teach to our teachers. Exactly. Yeah. To how to teach to the students. Yeah. That piece is broken because a professor that is focused on their own research area, they hate to teach, okay? And what they have learned was from, let's say, 10, 20, 30 years ago, they still keep on teaching, right? Yeah. That's something that we need to fix. Having said that, there are some schools which already have taken the action, okay. And then they're using the open source foundries. I think some of you may have heard about Skywater, which they do tape out. So I've seen schools are using the open source software going from RTL to GDS2 and then taping out on a really old technology, but still let the student to see from the full stack, right? Including the board. Though they don't do the board design, but still they get to bring up the chip, see what are the challenges in terms of working with the actual silicon, right? These are the things that needs to be advertised more in the more prestigious schools. Some of the schools that I've seen is students coming out of the programs, they only want to work on AI, ML, nothing else, nothing else. I don't mention a name, but out of 75 students in a program, on one of the best schools in the nation, all of them, without any exception, wanted to go to AI/ML. 10 years ago, it was only software. Now it's software with the specialization of AI/ML. That's what I see.
Do any of you other gentlemen have anything to add to that? Otherwise, we'll go to this question.
Thank you.
I would just on top of what Brett brought up about SysML version 2, which is really SysML version new, we've got the additional problem that there's been a lot of teaching of SysML v1 as a modeling language versus a systems engineering practice. And now we're going to have to get back to some of the fundamentals of systems engineering and rethink how we want to express our models in V2, which is a tremendously powerful event that's happening right now in industry.
Agreed. Agreed. So, sir, this is probably our last question.
Okay. Quick question. I'm a PhD student, and I think all the one here agree that the system level is important to the chip designs. But how come there is only one? At least I noticed there's only one topic in DAC related to the system level. So it becomes an AI DAC instead of system DAC. So I'm curious about how come, what's the problems, and will that be fixed or improved in the future for introducing such a system level issues to DAC or circuit design? Thank you.
Well, that would be more of a question, I would say, for DAC planning and organization. We address as much of it as we can, but it also depends upon what the state of the industry is and what the questions being brought forward. I believe there were 200 AI-oriented presentations at this year's event. A parallel could be drawn with display technology. I remember being at Society for Information Display 20 years ago, and they said, in 20 years, the LCD industry will own everything and everybody else will be meeting in a little room around the block. We're rapidly getting to a point where AI and ML are bloating and filling the room, but we don't know where that's going to go either. Any of you gentlemen have any, Brett?
We always see the hype cycles. That's all I can say.
So what I can tell you to short answer is I cannot talk on behalf of DAC, but I feel like where the funding goes, people follow, right? That's the same thing that's happening. See how much investment has been put into AI ML versus systems or other disciplines.
Now, we have like literally 3 minutes left, and I love to ask the crazy questions. And one of the questions I wanted to ask and get your opinions on, I realize it'll be short, but just a little short opinion on it, is what about leapfrog technologies? What happens when we get piezoelectric microcontrollers? What happens when we can have maybe more optical chip systems? Can leapfrog technology address Moore's law?
I've seen photonic chips in research, let's say 10 years ago. And even I've seen some research about it. It seemed promising, but I haven't used it in any of our chips. So I don't know if someone else has used it. Maybe too good to be true. Though photonics is good, not within the chip. Outside the chip, it's been used. We are using it as well. I think some of it is public, like how it's being used in the space.
Well, I mean, but like, for example, Mark, piezoelectric semiconductors are revolutionizing the power industry right now. Once they get qualified and used in more advanced devices, it could disrupt the industry from that angle. What do you think?
From my perspective, I think there's a lot of things we're going to have to use better to get after this problem. I don't see the silver bullet, though.
I don't think it's a silver bullet either. I think it might be a very strong tool. What are your thoughts, Larry?
I think maybe to address the question from the audience also is that systems are becoming ever more complex with more details, more maybe electromechanical elements, say in an automobile, or of course embedded software. Anytime we have a new and advanced technology like piezoelectric, we'll consume that too. It'll give us more compute power, let's say, in the same area. And so whatever I can't weigh in on that particular technology, but there will be other research and developments that will amplify our ability to solve and embed even more complexity into our systems. And for sure, that complexity is going to drive us towards needing a more model-based approach.
Brett, last thoughts on that?
I'll build on that. I just say whatever power you get, the software guys are going to figure out a way to use it. So I think we're always going to have a little bit of an issue there. I do think that means why you got to do the trades. You got to do this. We really have to get to the system model and be able to leverage it to see those trades over time.
Well, thank you, gentlemen. Okay, one more. What we ask your last question, sir.
From Siemens Research. I don't know whether you're familiar. Pictures of Future, that used to be the R&D magazine coming from Siemens. Very motivating. So now that Siemens is in the EDA with the acquisition, now I think quite a bit of time has elapsed. So Siemens has Industry 4.0 automation enabler with so many different tools and systems, platform for designing very complex automation systems to manufacture the very complex stuff, right? So how are you looking at systems to look at electronics and thermal and chemical, the multidisciplinary approach? Are you really, is it integrated truly into the company? Are you coming out with a true platform, with a homogeneous, developer-oriented? I think the way it has to be done is it has to be DevCon type of, the software world has done it very well. So how do you see this strategy for enabling developers to design complex systems now that you have many pieces together, especially Siemens, because you're in a unique position? I just want to know the thoughts. Yeah.
Well, I'm looking around to see how many of my bosses are here. No, I mean, it's a tough problem when you have a large organization with many different segments with their own challenges to stay in business and grow their business. Trying to find ways to build the collaboration, build the sanctioning. It's tough, and our execs hear a lot of different things from a lot of us, right? So it's a hard job for them too. But I will say we're making progress. We've made some really good decisions in the past couple of years, and I'm hopeful that we're going to be able to unlock this huge portfolio in a way that is going to make everybody happy.
Any last comments from anyone here? I'd like to thank everyone for taking the time to watch us. It has been I really enjoyed this conversation.
Same.
I hope you all enjoyed this conversation, and we'll see you next year at next year's day.